All right, probability review. You ready? Okay. So I'll go over some terminology. We'll try to work a few problems. We'll see how far we get. We can continue on this tomorrow. So a probability experiment is an experiment where we generate some random phenomenon. A random phenomenon might be rolling a die, and we do this random phenomenon many times. We roll a die, a six-sided die, many times, and we find a pattern in the outcomes of the die. In the outcomes. Okay. So, the pattern may be that approximately 1/6 of the time we get a 4. So, my random phenomenon, is any kind of like randomly occurring event where I can't predict from one roll to the next what that die is going to be. But there is a pattern, and I can predict what's going to happen if I roll the die many, 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 many times. An event is going to be some outcome of a probability experiment. So the event could be rolling a 6. The event could be rolling an even number, blah, blah, blah. The sample space is the collection of all possible events. And the probability of the event is the number of outcomes that are wanted divided by the total possible outcomes. Remember, when we're talking about probabilities, we're not talking about what happens on the next roll, the next sample that we pick out. We don't know what that one's going to look like. We are talking about what happens in the long run. And that we're talking about the law of large numbers. So if we do the probability experiment, many times, we get an average number of outcomes that represents the probability. Of an outcome. Complement of an event is anything but the event. Complement of rolling a 4 would be not rolling a 4. Complement of event A is sometimes abbreviated with that superscript -1. It's also abbreviated with a little squiggle. Anything but the event? If we do a probability experiment many times, boy, many times, we get an average number of outcomes that represents the probability. Boy, writing too fast. Addition rule. Okay, we add probabilities if we look at the language of what's being represented to us in a problem that has the word or if we think the word or makes sense in a sentence about two different events. So if I want event A, I want to know the probability of event A or B occurring. That is probability of event A plus the probability of event B minus the probability of event A and B occurring. So if we think about this in a Venn diagram, there's event A, there's event B. What happens with this part that is both A and B together is if I add all of event A and all of event B, I have counted that little green section twice. I can't count it twice, so I need to subtract it off once. That little green section is the A and B part. Subtract it off once because I've double counted it by just adding. Yes. Yes.
So when you subtract between A and B?
When there is an intersection.
Yeah, but is it A times B?
So it is often A times B. And we'll do that with the multiplication rules. So if there is no intersection of these events, that's called mutually exclusive. Events that cannot occur at the same time. So you the probability of so the event A is that you're under 21. The event B is that you're over 45. You can't be both. And so since the probability of A and B occurring, since there's no intersection here, that probability is 0. So this simplifies my addition rule. When the events are mutually exclusive, I don't have to subtract that little bit off because that would be 0. There is no intersection part here. Okay. Multiplication is when we list two events and we think the word "and" as a connector between the two events sounds correct. So probability of event A and B. So the probability of A and B is the probability of event A times the probability of event B if A and B are independent. And conceptually, independence means that the knowledge that one event has occurred doesn't affect the probability of the other event. So I'll write down here knowledge. So we've done tests of independence. And that's when we're sampling. We use that significance test of independence. But but in probability language, we're not doing a significance test.